Thanks for the introduction, Kevin. So this talk is still part of the beginner track of this workshop. So we'll cover basic things about Lean, and during the exercise session that will be most of this morning session as yesterday and as all week long, we'll go through the tutorials files, but first I need to explain some context and about Lean and a couple of basic things. So we need to talk about foundations. So of course the key point is we don't want to see foundations, right? The topic of this workshop is about using Lean or any other proof assistant as a general purpose tool for mathematicians. So if as a mathematician your research topic is foundations of mathematics, then it's great, and of course you want to talk about foundations. But for most of us, we just don't want to talk about foundations. We want to do mathematics, and we also don't want to talk too much about philosophy. If you're into philosophy, it's also very nice, but this is not the topic of this week. So ideally, our proof assistant shouldn't have us caring about foundations. But as Johan explained yesterday, this ideal proof assistant does not exist today. There are many things that are not as we wish in current day technology proof assistants. So today we need to talk a bit about foundations. And we don't really care about whether this is something deep about the nature of mathematics, but currently if we want to talk about mathematics, which is already a much more concrete goal compared to understanding what is mathematics deeply, we need foundation. So we have a standard lie for this. So we know we don't use foundation actually, but if cornered, if people ask us, we mumble something about maybe first order logic and ZFC set theory. And of course, we don't know about ZFC axiom, at least I don't know. And we could have a poll here asking how many people in the audience can list ZFC axioms. But the key thing is in such foundations, everything is a set. So there is only one kind of mathematical object, which is called a set. And there is the equality symbol and the membership symbol and nothing else. So of course, the set of natural number is a set, but the exponential function is also a set. So it's a set of pairs of real numbers, such that the second member of the pair is the exponential of the first one. And pairs of elements of sets are not a basic piece of set theory. So you need to encode that into set theory. And even stuff like structure, a group structure on a set is an ugly set, and I just don't want to show what it looks like. Let's see what Kevin mentioned yesterday in his talk. So natural numbers encoded in set theory. So the standard way to do that, as Kevin said, is using lots of empty sets. So you just declare 0 is the empty set, and then the successor of a set of a natural number is this natural number union the singleton set containing this natural number. So 1 is 0 union singleton 0, and so this is the set containing only the empty set, and then 2 is this set, and 3 is this set, okay, and so on. So these are natural numbers in ZFC set theory. One way to encode piano arithmetic in ZFC. And now, nice exercise. So 3 is a topology on 2. And note also that the intersection between 2 and 3 is the set 2. And the set 2 belongs to the set 3. So those are all nonsensical statements that are pure artifact of how everything is shoehorned into set theory, right? And we know we shouldn't say that 3 is a topology on 2, but there is nothing in the foundation preventing us from doing this. But this all rely on a gentleman agreement, okay? So this is what are the official foundations of mathematics. And this is not good enough for a proof assistant. I mean, there are proof assistants using ZFC set theory as foundations, but they typically lack many nice features, automation and stuff like this. So we use something else in almost any proof assistant, and in particular in Lean. So I need to say something about type theory. So the key idea is every meaningful piece of mathematics has a type. So this having a type is denoted by a colon. So 2 has type nat, natural number. Exponential has type function from R to R. And this is a function x maps to x times exponential x is a function from R to R. So it has type R, arrow R. And mathematical statements also have their own type. They are prop, like proposition. So 1 + 1 = 2 is a proposition. It has type prop. And things like 2 intersected with 3 or 2 belongs to 3 have no type at all. They do not type check. Okay, so they are, you cannot state this in Lean, for instance. So we can check that you cannot state this in Lean. So a bit of terminology, those pieces of mathematics, they are called terms. And so we have already seen the word type. And in Lean, you can ask what is the type of a term by using the command sharp check. So we can in Lean here. Johan, can you see can we see what I'm screen sharing or not?
Yes, we can. Maybe
yeah, you can see VS Code right now?
Yes, we can see VS Code. Maybe you can increase the font size a little bit.
Yeah, sure.
Okay, this is perfect.
So you can see I asked check natural number, and the answer is here. It says natural number is a type of mathematical object. So it's a bit unfortunate that we have capital T type, which is the basic of data types, and what I use as a lower T type is not quite the same thing. But so let's move to the next example. So the real exponential function is a function from R to R. So this is the type that Lean's reports, and the same. So this same thing. Remember on my slide, it was written x maps to x times exponential x, and this is the computer scientist way of writing this. So they write lambda x, comma, or sometimes dot, but in Lean it's exponential x. So this is exactly the same thing. And for historical reason, they use this lambda. And since functions has a very important role in this whole story, the whole theory that everything relies on is called lambda calculus. But it really means maps to. And those kinds of things, creating a function like this is called lambda abstraction, if you meet this term. So, okay, so this is indeed a function from real number to real number. And if I try to check 2 intersect 3, just fails. Okay, there is a red squiggle here and an error message here. And the same would have check 2 is in 3. So notice Lean is not complaining that this statement is not true. It's complaining that it cannot make sense of this statement. Right. So now we have typing. I mean, Lean gets all this information about what is the type of what by using rules, typing rules. And for instance, a very important one is if you have f with type function from x to y and small x, fx, which is f applied to x, but we don't need parentheses here, but in normal math, we would put f parentheses x. There is a typo on my slide. It has type y, of course. So this is. Oh, by the way, the slides you can find on the website. I should have said that. If you look at the schedule of you've got a link to the slides, but you will have the typo in the current version of the slide. So I meant to write f of x as type y. Sorry about that. Okay. Now, there is something that, again, we shouldn't have to care about, but have to care about a little bit, is the distinction between what is in the theory we are talking about and what is in the meta theory above. So an assertion like x has type t And the typing rules, like the one that had a typo on the previous slide, they are not something you can prove or disprove inside the theory. Just like you cannot prove the rule of first order logic when you're working inside the ZFC set theory. So they leave one level up in a meta-theoretical world. And now this word meta is dangerous. I mean, the computer scientists, they use meta, or logicians, they use meta as soon as something is slightly weird. So they can use it with very different meanings. People who have attended, who have watched Rob's videos about meta programming yesterday already saw at least 3 meanings of the word meta. And this is one more that I think was not used in Rob's talk. Sorry about that. Okay, I mean, you can interrupt me with questions. I don't know, people are very quiet in Zoom. And of course, it's not an issue if this is going a bit too fast. I mean, the first step in understanding anything is just getting used to words, and so you're just hearing if you are hearing those words for the first time, you're just in the beginning of getting used to hearing those words, and at least you know they exist, and you can ask questions when you think that you're stuck because of what I'm explaining currently. So also in the meta-theoretical world, live the conversion rules or the reduction rules. And those rules, they assert that some terms, so some meaningful pieces, some pieces of mathematics, can be definitionally equal. And this is a notion that doesn't exist in real-world mathematics. It's just specific to those foundations that we are using. So, for instance, the very first of those rules is the alpha conversion or alpha reduction rule, saying that if you've got a bound variable, so this x here is really, remember this is notation for x maps to x plus 2, and this is the very same function as y maps to y plus 2. And in a very strong sense that is indicated by those this strong equality here. And I won't list all the rules, but for example, the next one says what happens when you apply such a function. So if I apply x maps to x plus 2 to 3, then by beta conversion, this is 3 plus 2. Just replace x by 3 everywhere it appeared here. Okay, but again, the fact that this is an equality is very strongly built into the logic framework that we are using. And of course, there are also rules saying that you can unfold definitions. And for instance, the fact that in natural numbers, so S is this successor function that Kevin explained yesterday, 3 plus 2 is equal to 5, but this is not an equality that you have to prove inside the theory, because it really follows from unfolding the definition, and this delta reduction rule tells you that those are equal by definition, which is again a stronger notion of equality that has no analog in informal mathematics, and has no analog in formal mathematics based on other foundations. Okay?
Patrick,
yes?
Isn't everything just followed by unfolding definitions?
No, I mean, sometimes I mean, in the end, when I mean, I will come to this in the next slide, but when Lin checks theorems, you could ask it to unfold all definitions, but it would be awfully slow. I mean, actually, it does operate at a higher level than that. So no, it's not always unfolding everything down to the basic definitions. When you apply a theorem in Lin, I mean, if Lin got convinced at some point that this theorem holds, it won't unfold the proof again each time you want to apply the theorem.
So what's the difference between repeated delta conversion and like other proofs? Something that is not definitionally equal.
Well, if you want to prove something using an equality which is not definitional, you need to use rewriting, and this won't happen automatically. But I mean, it's a bit hard to answer a question like this abstractly without just completely blowing up the time schedule. But you'll see while using Lean, really the goal of this slide is just making you aware that something slightly unusual exists in this direction. And then when it comes up in practice, we will be able to discuss more. Okay. So what about proofs? So we've already seen that a mathematical statement is something that has type prop. But if P has type prop, then P itself is a type. And you can have a term H with type P. And what is such a term? It's a proof of P. So this is really a key concept. If P is a mathematical statement, it is a term, it is a type of its own, and terms having these types are proofs of P. So note the statement that P implies Q is a function type. It's a function from P to Q. And it's also a proposition. And by the function typing rule that we saw, if H has type P to Q, and H sub P has type P, then by the function typing rule, when you apply H to H sub P, you get something that has type Q. So really, from this point of view, H, which is a proof of P implies Q, is a function turning a proof of P into a proof of Q. This is just a nice trick. And there is also predicates. If you've got a function from X to prop, so this is a predicate on the type X. Given any element of X, it gives you a proposition, so something that could be true or false. Then you can form a new term, which is for all X, Px. This is now an autonomous mathematical statement, a prop. And this is also something like its inhabitants are also some kind of functions. If you've got H, whose type is for all X, Px, and some specific X0 having type X, then when you apply H to X0, what you get is a proof of Px0. Okay? So H behaves like a kind of function here. But note it's a slightly weird function because its target type depends on the value of its input. So this is why we talk about dependent type theory. So there are other aspects to this Lean being based on dependent type theory, but from our point of view, this is actually the main one from this discussion of foundations. Okay, so you will see all this in practice, but just keep in mind right now that those things. So a term of type P, if P is a mathematical statement, is a proof of P, and the fact that implications are really encoded as functions, and for all quantifiers are encoded as kind of functions too. Okay, so you see now verifying a proof is a special case of type checking a term. So we already asked Lean to check that some formulas as a given type, but when Lean checks a proof, it's actually running a special case of doing that. Okay. So what else? We need to have a way to build types, and we've already seen that if we have types around, we can build function types. But we need something to start with, some basic types to start with. And Kevin already explained yesterday how the natural numbers are built as an inductive type. So I really don't want to discuss details here, but this kind of definition that nat is an inductive type, and there is those vertical bars mean there are two ways of building a natural number, either using 0, and this will give you a natural number, or taking the successor of a natural number, this will give you a natural number. So this was covered yesterday, but actually, all the logical operators that I haven't discussed yet are also constructed like this. For instance, the logical OR, saying that either proposition A or proposition B is true. I mean, there are two ways to construct a proof of A or B. Either you provide a proof of A and you get a proof of A or B, or you provide a proof of B, and this is also a valid way of proving A or B. And the same for existential quantifier. The existential quantifier is also not part of the meta-theoretical world. It's just defined inside the theory by an inductive type too. If you want to prove that there exists some A such as PA, then you need to provide, knowing that P is a predicate on alpha, you need to provide some witness, which is a term having type alpha, and a proof that P, so the witness is W, and a proof that PW holds. And this is how you prove that there exists W such that PW. Okay, and so those inductive types, when you define them, you both define how to construct them and how to use them. This is, you see, for natural numbers, this definition also tells you that you can construct functions out of natural numbers by recursion. And actually, there is the same story for all the inductive types declarations. But you don't need, you can do the whole tutorial without ever caring about how those things are defined. We just wanted you to let you know that there are answers to those questions. Okay, and I have a couple more minutes. I wanted to talk for half an hour at most to tell you something about elaboration, which is the other piece of things that could be puzzling at first. So remember from Scott's demo yesterday, we had this theorem, infinitude of primes. And the theorem is written in a way that lets Lean work even to make sense of the theorem. And it's very important that we can do that because we really want Lean to assist us, not us to assist Lean, at least not too much. So Lean needs the types of n, it's not given anywhere, and the type of p, and it needs to figure out an order relation to make sense of this p bigger than n. And very quickly, what happens is that Lean goes through this expression from left to right and just tries to figure out missing information as it goes. And when there is not enough information, it creates some hole that is named a meta variable. And then try to make progress. So in this case, what happens is when it sees n, it has no way to figure out what is the expected type of n. So it creates a first meta variable, question mark m1. When it sees p, there is another meta variable, question mark m2, which is created. And then when it sees p is at least n, then it deduces that the two meta variables m1 and m2 have to be the same because the inequalities are only among terms with the same type. And also take note that it will need an order relation on this mysterious type n1. And then when it reaches nat.prime p, because nat.prime is a predicate on natural number, it understands that all this makes sense only if p has a type nat. And now every types are discovered because we already knew that n and p need to have the same type. And then it goes on looking up a database to know how the order relation should be found on natural number. And this will be the topic of one of tomorrow's talk, this database thing. Okay, if you really want it, you can ask Lean to tell you everything it's doing while checking this statement. So while just trying to make sense of this statement, I'm not proving it, and just showing this so that you know it exists. You don't have to read anything, but you can see that Lean is visiting stuff and it has questions, and you see those question mark M1 appearing, and you see, for instance, this is the place where it realizes that M1 has to be the same as M2 and so on. Okay, so but as a Lean user, you never need to do that, or if you need to do that, it means you're in trouble. Okay, I don't even know by heart what are the magic incantations here. I need to look them up, right? And one last thing is during elaboration, sometimes things do not make sense unless you use some inclusion map. For instance, in this statement, for all x real number, for all epsilon positive, there exists a natural number such that x is less than n times epsilon. When it comes to multiplying n and epsilon, because epsilon is because x is known to be a real number, then this inequality sign is the inequality on real number. So on the right-hand side, we need real numbers, and n is not a real number, it's a natural number. So Lin is cornered here and just tries to look up in a database whether there is an inclusion map or a coercion map from natural numbers to real numbers. And this is what you will see in the, so Zoom is hiding part of my, this is what you see in the tactic state here as this funny up arrow here. This little up arrow, it's little because it's meant to be almost invisible, but not quite. You mean you can ask Lin to make it fully invisible, but this is not recommended, unfortunately. You still need to be somewhat aware of the fact that this inclusion map has been applied. But this will be the topic of one of this afternoon talk. And if I click on this, you can see there have been a coercion applied from natural number to real number. Just ignore the other pieces. But at least VS Code is telling you what is this funny up arrow. So this up arrow n has type R, and it has been obtained by applying a coercion from n to R. Okay.
Can I ask a question?
Yes.
From there, so you told it that x was a real number, but you didn't tell it that epsilon was a real number, and yet somehow it deduced that epsilon also had to have type R.
Yes, because so again, Lin is going from left to right.
Yeah,
so,
but when it first sees epsilon, it
so
could
it
be
sees x. It sees x before seeing n times epsilon.
Yeah.
And because it sees x, it deduces that this inequality is inequality among real numbers, and then this forces n times epsilon to be a real number. So the multiplication has to be multiplication of real numbers, and so epsilon that we knew nothing about until now is now forced to be a real number, and n is also forced to be a real number. But since we already said it was a natural number, Lin inserts the coercion.
Yeah. So the zero, when it first meets the zero, it doesn't know whether
no, it doesn't know which
natural
zero
number
it is.
And the greater than.
Yeah.
It just knows that epsilon has a type that includes a zero.
Yes, exactly. So when elaboration reaches that part, Lin takes note that whatever the type of epsilon is, it has to have an order relation. I mean, at least a pre-order relation and a zero. But that's all. This is registered for later investigation.
Okay, good, thanks.
And sometimes you can encourage Lin to insert coercions by writing so-called type ascriptions. But I don't want to discuss that too much because I'm running over time. I really want you to play with Lin and ask questions rather than attending lectures. But you can do that, so we can just maybe very quickly check that it works. If I've got somewhere in the environment, I declare that if you need some n, and I don't tell you anything about n, then it should be a natural number. Then if I do this, this is indeed a real number, and n has been coerced to a real number. And 1 is also the real number. We can even play with two natural numbers. Maybe it's clearer this way. And look at 1 over n plus m. And you see that because we really insisted on the fact that n plus m should be a real number, then addition has to be addition of real numbers. And when Lin gets to the argument of addition, and they are natural number, it inserts coercions everywhere. Okay? But really, for what matters for today is, you know that those funny up arrows, they are somehow inclusion maps inserted for you by Lean. And all the other details are, you don't need to care about to make progress today. Something else I wanted to do right now is just quickly show you the community website, because I think it was not explained yesterday. So if you look for Lean Prover community in your favorite search engine, you'll end up on this website. So hopefully you already managed to install Lean and learn how to work on Lean project. But you should really know that there are also learning resources here and listing lots of stuff, including a tactic cheat sheet that you may want to print or have around this week. And also, maybe if you want to search for things, the library overview could be useful. So this is a rough overview of what the MathLib, which is Lean's mathematical library, mathematics and computer science actually library, knows about, and it just gives you quick exploration entry points if you want to know, I don't know what, if I click a random things, if you know what is the definition of a module, then you can jump to this documentation here. You can see what is hidden in this documentation. You can jump to the source code on GitHub and just look around. If you are looking for things inside VS Code, I mean, Scott already showed a couple of tricks, but there are even more basic things. Like if I do Control-Shift-F, I can search through files. And for instance, if I want to know about the Einer theorem, you can just do, this would just do a regular search in all files that are around and just find stuff. Okay. And I think, yeah, no, I need you to be ready to start using the Lean tutorial. So I need that you are able to just get the tutorial. So I just, I don't know if I can put this bigger. Yeah, probably. So I can download the tutorials project like this, if you haven't done so already, and it will download a bunch of things, including ready-to-use MathLib. And then inside the tutorial, we need to make a fresh copy of the exercises so that they don't get overwritten if we update the tutorial. So I will create a copy called my exercises of this tutorial / SRC exercises, and CP-R. And then code tutorials should open this tutorial. And I want to go to this file explorer here, open SRC, open my exercises, and you can quickly look at this file if you want, but the exercises really start in this equality rewriting.lean, and you can see that right away after maybe 1 second you are ready to prove stuff. I mean, if you see orange bars for a long time, it means something went wrong and you got half the setup you should have. If I restart Lean, which is sometimes useful when things go wrong, so I can do Control-Shift-P and type Lean restart until I find something interesting. You can see the orange bar just were there for 1 second, right? I could just redo it again because it's very fast. Look at the side of the screen. So Lean is thinking for 1 second and then it's ready to prove something. So since you've played the natural number game yesterday, the first exercises will be a piece of cake. You probably want to skip these exercises. Probably the new thing start here with calculation blocks. So if you are not familiar with this, this way of telling Lean about a calculation, then you need to start here. So now we'll split to breakout rooms like yesterday, and you'll work on those tutorial files. And at the end of the morning, you'll try to report on where you are, and so that we can continue this afternoon, and so that Jeremy will talk this afternoon, know where you are. And of course, you'll work at different speed, but we need to know roughly where people are. And please don't hesitate to ask questions to people who are with you in the breakout rooms, and share your screen as soon as you're stuck. This is really the added value of doing that this week with us, instead of just downloading Lean on your own and playing the tutorials without any people around. So oh yeah, maybe one last point is if you are interested in Lean for teaching, because this is one of the possible uses of Lean, just teaching students what is a mathematical proof and rigorous proofs, at least this model of what it means to prove something. You should know that these tutorials is almost exactly what I used for teaching with first-year undergraduate at Orsay this year. So it really comes, it is a second incarnation of a set of exercises that I used with first-year students that had a calculus course, including definitions of limits with epsilons and deltas during the first semester, and then during the second semester, they were playing Lean with me and Frédéric Bourgeois at Orsay. And that's all I wanted to say.
Okay, thanks a lot, Patrick. So, yeah, I'll pause a moment to see if there are any questions right now for Patrick.
Mm-hmm.
Could you say something about the lambda construction?
The lambda abstraction. So let me go back to lambda. So do you agree that we have something like this in real mathematics, saying, let's consider the function x maps to x times exponential x, right?
Sure.
But interestingly enough, we don't have a name for this construction. I mean, when you start using a proof assistant, and especially if you have teaching in mind, it's very interesting to see that there are many basic operations of mathematics that we simply don't have a name to talk about them. And a very easy corollary of the fact that we don't have a name is the fact that we don't really teach them. We just assume that students will get used to doing this. So students will get used to constructing a function by writing x maps to x times exponential x. But if you're interested in logical foundations, or if you're interested in explicitly telling the students what are the rules of the game, then you need a name for this construction. And okay, the people in logic call this lambda abstraction, but this is only a name. So abstraction, because if you only look at the right-hand side, x exponential x, you can see x is somehow concrete. It assumes you've got a real number x, and you take the exponential and multiply by x. But after putting this x maps to in front, it becomes an abstract x. This is why it's called lambda abstraction. And again, I'm not saying that as soon as you teach mathematics, you should talk about Lean, lambda abstraction or type theory or anything. I'm just saying that it's interesting to be aware of the fact that we don't have a name for this construction, which means that we are hiding something. And if we consciously decide that we want to hide this and don't provide a name for this construction, it's perfectly fine. What I'm saying is that you're better off as a teacher if you are conscious of the fact that you don't have a name for something, and decide that you're happy with it, or decide that you are not happy with it. Okay?
But this exactly specifies a relation, which means which actually is a function. So what do you add by calling it a lambda constructor as opposed to a function, a map, or a relation?
Well, I mean, the function is is a kind of object. So depending on your foundation, is either an object with this typing rule that is written here with a typo. So I don't know. I need a bigger mouse cursor to hide the x. Or it is a relation, so a subset of x times y. Okay, but this is the notion of function. But how do you build a function? This is the question. I mean, either you build a function using a lambda abstraction, or you build a function by using operations on function. For instance, you could build a function by composition, or you could add two functions. I mean, there are more sophisticated way of building a function. But the very basic way of building a function, which was historically the only meaning of the word function, is to give a formula that computes the output values in terms of the input value. And this basic construction is called lambda abstraction.